we are going to solve another interesting problem, number 2594, minimum time to repair cars. And in this problem we have been given one rank array which depicts the rank of n mechanics, and we have been given through some cars which we want to repair, and we have been given one problem definition that a mechanic with a rank R takes R into n square minutes to repair n cars, and we want to return the minimum time taken to repair all the cars. So just by looking at the problem, what we can observe is we have one function of time R into n square, and we want to minimize this time to repair all the cars. So what I will do is I will first find the time to repair one car and time to repair one car, maximum time to repair one car and minimum time to repair one car. So the minimum time to repair one car would be the minimum. So if the worst rank mechanic start working on one car, so and it will take integer minute, minimum is 1 to repair this car, and the maximum time to repair one car is if the all the cars are repaired by the best mechanic, so which is the car square as per the problem definition. So this is our maximum and minimum time, so which we can assign over here. So this is, for this first example, this is 4 into 10 square, which is 400, and this is 1 into 1 square, which is 1. So between 1 and 400 our minimum time lies somewhere, which we have to find. So what we observe is this is a problem function, and here we have time, and this is the number of cars that could be repaired at a given time, which is a function of time, which we can write as t by r square, t by r under root. So we see that this is a monotonically increasing function, and this function we want to reach to a we need to find the optimal time where all the cars could be repaired in minimum time. So we need to find this t minimum when the car is 10 for this case, and it could be different for other cases. So what we'll do is we'll apply a standard binary search. We'll divide the section in two halves. So first we'll divide it in mid. We'll check what are the number of cars required to be repaired at this time of mid, which is L plus R by 2. So, and we'll compare this mid value of car with the total number of cars, and we can see that this region, this mid, is less than the number of cars, and if this mid value of cars is more than or equals to the total number of cars, then we have to move our boundary accordingly. So we see that today this number of cars is less than the mid value, so we need to update our right pointer towards the left. So we'll move this, so we'll update our R towards the mid, and when our mid is less than car, so we'll update our L towards the mid, and this will do until we have exhausted both left and right, and in the end we'll be meeting at this value with the left boundary. And one thing we also need to do is we need to calculate our mid function. So how will we do that? So it has been given the definition of mid. So That is basically we need to find all the cars that could be repaired at this mid time. So that is mid floor values, basically under root of mid of R1 up till this. We have exhausted all the list in the ranks. So this is n minus 1. So in short, we can write a summation of mid by Ri, where I is between 0 to n minus 1 for all R belongs to rank set. So now let's get into the coding part and we write what we have seen. So now this is how we can write this function. Okay, so first we'll define our left and right boundaries. So left is minimum and right is maximum. So this is the minimum of rank and the 1 square and the maximum of ranks and the total values of car that we have, then that square as per the problem definition. And we'll start our binary search until we have seen both, until we have exhausted both left and right or our left and right mid. So we'll calculate the first the mid values, which is L plus R by 2, and then we'll compare the function value of mid with the total number of cars that we have, and we'll update left towards the mid if it is less than, otherwise we'll update our right towards the mid. And in the end we'll return the left boundary when both L and R would meet. And now we need to write our small definition of problem function, so which is define f of time, and which will give us the number of cars that could be repaired in a given time t. So we'll need to find this. So this is, like we discussed, the floor of the values of time that we are finding, and it is the square root of the time for all R in the rank set that we have, and we'll return this n, and we'll compare this time with the cars that we have. Now let's run our code and see how it performs. Okay, so it has been accepted for all the example test cases. Now let's submit our code. So it has been accepted and it's fast, and the time complexity for this is O of n times log of the upper bound minus lower bound that we have. So O of n is for running the for loop in the time function that we have created, and log of R minus L is for the binary search that we have. And the space complexity is O of 1 because we are not using any space. So this is how we solve this problem. And if you like my solutions, please like and subscribe to the channel. It helps, it motivates me to keep bringing such more awesome content for you guys. Thank you. Have a nice day.